Hello everyone, and in this video we're going to be talking about how you apply the fundamental theorem of calculus to evaluate angles. All right, so let's recall what the fundamental theorem of calculus says. So part one of the fundamental theorem of calculus says that if you take an integral from some value to an unknown value x of a function f of t dt, well, yeah, you to evaluate this you can take the antiderivative of this function. And it's going to be in terms of x, because since we don't know x, depending what x is, we have to adjust our answer. But what part one says is that, so there exists an antiderivative that will give us the area under the curve. But if we take the derivative of this function, which is equivalent to saying take the derivative of the antiderivative of f of x, what that'll give you is just back to the function f of x. So the original function f of t dt, but instead of t, basically you replace it with a x. And that's kind of the idea of part one in a nutshell, is that when you take the derivative, it's just this function evaluated at x. And then part two of the fundamental theorem of calculus is really used to evaluate these. So if you want to evaluate a function f of t dt from a to b, where a to b are both real numbers, so now we have a set area under the curve we want, well then what you can do is just take the antiderivative of the function and evaluate it at the upper and lower bounds. All right, also known as the area function. So this will give you the antiderivative of b minus the antiderivative of a, and that will give you the area under the curve of the function f of t on that domain. Okay, so those are the two parts. And then recall what an antiderivative is for polynomials. Now, you've gotten to a point now where hopefully you've picked up on the pattern. So if you have a function ax to the nth, if you want the antiderivative, well, you add 1, and then you divide by that number. So it's ax to the n plus 1, then you divide by that number, or, if you want to write it as a fraction, a over n plus 1, x to the n plus 1. Because again, if you take the derivative of that, well, that comes to front and multiplies, which will cancel and just be left with a, and you subtract 1, which will be left with n. So you go back to the original function f of x. Now let's apply all of this information up here to several examples down below. Example 1, find the area under the curve of 2x to the negative 3 from 1 to 3. All right, so we're going to apply the second part of the fundamental theorem of calculus, which is a definite integral here. So we take the antiderivative, which is going to be x to the negative 4th, and then you divide by that negative 4, and then we're going to evaluate it from 1 to 3. And that's the notation we use. Now I'm going to clean this up before I do this, so let's clean that up as just negative 1/2 x to the, oh, I made a big mistake. Oops. And this is a mistake that hopefully you're like, Mr. Hein, you're not doing it right. If you add 1, it's not negative 4. If you add 1, it's negative 2. Right? If you add 1, that's negative 2. In which that actually gives us just negative x to the negative 2 from 1 to 3. And we evaluate that, and I like to always use parentheses for each bound so I don't get confused with the positives and negatives. So you have negative 3 to the negative 2 minus negative 1 to the negative 2. Well, remember that's dividing by that number twice, so that's really, negative 1 over 9 minus, well, that's just 1, and that's negative 1. So you get negative 1/9 plus 1, which is really plus 9/9. So the answer here is 8/9. There's the answer for that first example. Example 2. Now we have a stretch in front of it, a multiplier or a constant, so 2 times all this. So when I write this, it's 2 times, and then we're going to evaluate this. So the antiderivative here, if I was to rewrite this as 3x to the negative 2, is going to be 3x, add 1, so that's negative 1 over negative 1. And that's to be evaluated from 1 to 3. Notice how the 2 I keep outside of all of it to make sure I save that till the end. So then if I plug in 3 here, so that's just really -3. So then I'm going to get 3 times 3 to the -1 minus -3 times 1 to the -1. Keep going. 3 to the -1 is 1 over 3, so that's just going to make -1. This over here, that's just 1. So -3 and negative will make that +3, in which that's 2. 2 times 2 is 4, and there you go. Right. It's important to know how to do these by hand because there will be non-calculator questions like this. But for our purposes, they don't tell us that here. So if we want to evaluate on a calculator, let's just see if I got the second one right. Remember, you go to Math, scroll all the way down to Function Integral, plug in everything you had. So actually, before all this, there was a 2. From 1 to 3 of 3 over x squared dx. And hopefully we get 4. We do. And that's, good way of knowing that we did it correctly. All right? I know, puppy. I'm going to get you soon. This video is not long. Okay, so there's applying the second part of the fundamental theorem of calculus. These are definite integrals. Definite integrals. And again, that word definite just means bounded. Okay. Now, down here, we're going to be applying and that's part 2 of the fundamental theorem of calculus, by the way. Now, if we apply part 1 to some of these and just make sure you understand it, we'll see what happens. So what's the derivative from the integral of 2t minus 4 dt from 5 to some variable x? Now, remember that to do this, we would have, I'm going to skip a few steps. Well, this right here is actually the first part of the fundamental theorem of calculus, where if you take the derivative of an antiderivative for some value we don't know, what happens is you can just evaluate this function at x. So that gives us 2x minus 4. And it's really that easy. But for you, like saying, how did you do that, Mr. Ryan? So we take the antiderivative of 2t minus 4. So call this f of t, right? So if we have the derivative, and then we're going to take the antiderivative of ft, so then we'll have f of t, and we'll evaluate it from 5 to x, knowing what we know how to do, right? Well, that will give us the derivative, and then we evaluate its bounds, f of x minus f of 5. Well, when we take the derivative of f of x, you have f prime of x minus, and the derivative, well, that's just a constant, f of 5, you plug a number in, so that's going to give us 0. And remember, the derivative and the antiderivative are inverses, so that just gives us f of x, which you'll see is 2x minus 4. It's f of t, but with x plugged in. So a little bit longer of an explanation, but helps show you how I got that answer. For this example here, now the derivative's on the inside side. Can you apply this? No, you can't. That's saying something totally different. We always work inside out. So then this is going to be 5 to the x. The derivative of 2t minus 4 is just 2. And now we're evaluating the area under the curve of just 2 dt, which the antiderivative of 2 is 2x. And we're evaluating from 5 to x. So then that's going to give us, and notice this is why the notation gets kind of weird using x. I guess I really should have 2t here because it's in terms of t, sorry. And then value at x, you have 2x minus 2 times 5, which is 10. And there's the answer here. All right, trying to get through these last two so I can take my dog out. The derivative of 10 to 15 of 2x minus 4. So then we have the derivative, and this one, notice the derivative, and you think, okay, I can just plug it in, but wait, that's not a variable x like this example was up here, so it doesn't quite work the same way because we know where we want to find the area under the curve. Well, notice if I call this f of x, and if you take the derivative of all this, well, this, you're going to take the antiderivative of f of x and evaluate from 10 to 15. But notice that when we do the antiderivative of 15 minus f of the antiderivative at 10, well, this is just a constant, that's just a constant, and the derivative of a constant is 0. Okay. And then for the last one, notice that this is an indefinite integral because it's not bounded, right? It's not bounded. So here, what's the antiderivative of sine of x? Well, that's negative cosine of x. But for indefinite integrals, remember that we're not valuing the area under the curve, so we're just asking about an antiderivative, in which there's infinitely many antiderivatives, so you have to put the plus c. And there you go for the last one. So I hope that helps you see how we apply the fundamental theorem of calculus. I'm going to go now to take my puppy to the bathroom. Good luck on the assignment. Bye-bye.